Elva, are you recording?
I'm recording now. The talk may begin.
Okay. Good evening. It's a pleasure for me to to give you this talk about an introduction to analytic combinatorics. And I would like to start very briefly to dedicate this talk to Philippe Flageolet and Walter Kunter. I mean, the short story is that when I did my master in computer science in the 80s in Venezuela, Walter was my advisor, and there is some echo. Sorry.
Sorry, could everyone else mute themselves, please?
Okay. So, and we work on a problem proposed by Philippe Flageolet, and thanks to that paper, 25 years later, I started my PhD, and that's when I learned about analytic combinatorics. Okay, so I'm going to show very briefly a counting problem and traditional solution, and the plan is to then explain whatever I need about analytic combinatorics, I mean the basics, so that I can show you the analytic combinatorics solution to the same problem. Okay, and then I'll end up with a couple of recreational problems where I will explain a bit more of other other techniques. Okay, so the counting problem is one that Euler wrote to Goldbach back in 1751. And okay, so so here I show the first terms of the sequence, and so I think it's clear. Now it's very convenient for the counting is to define also t sub 0. I mean, you could think that there are 0 triangles here. I mean, that's why the index is 0. But there is one way, which is no triangles. I mean, that's why t sub 0 is equal 1. Okay, so the subindex tells you the number of triangles, and the value of t tells you the number of ways that you can split the polygon in triangles. Okay, well, maybe you know this problem is pretty old. So the way to tackle is divide and conquer, and you can analyze taking the base side, like analyzing the different possible triangles that can contain that base side. So for the hexagon, there are 4 triangles, so we have 4 cases. And then you can think, well, for each of them, how many triangles are on the left and how many on the right? And you can see that, and because those two are independent decisions, you get a multiplication. That's now you see why it's convenient that t sub 0 there. So, well, with that we can compute the value of t sub 4 based on the previous values. Well, and that reasoning leads us to this recurrence where, well, here I'm showing like the generic case where you have t sub I triangles on the left and t minus 1 minus I triangles on the right. Okay, then one way to solve this is using the generating function of the sequence, I mean, which is a formal power series. And then, well, you do some algebra, and you get to the functional equation for the generating function. Then, well, you can solve this using the quadratic formula, and you discard one of the solutions because if you put set equals 0 here, with plus the 2 sides are different, so you discard that. And well, again, Newton's binomial formula, binomial theorem, and some algebra gives you a closed expression, I mean, a closed formula for the sequence. But well, it's a bit not nice, but you can do more algebra and get to a nice formula for it. Okay. And these are the Catalan numbers, which are named after a Belgian mathematician, Eugene Catalan. And these Catalan numbers appear in variety. I mean, in combinatorics, they appear in many places. Here are just some examples taken from one of the books by Flageolet and Sedgwick. I mean, so yeah, what I was talking about was the triangulation, but these numbers appear in many other counting problems. Now, in many practical applications, we want to know more than the closed formula. We want to know the asymptotics, an asymptotic expression for it. In this case, Stirling's approximation formula for the factorial allows us to get there. That's just a simple application of that formula gives us this asymptotic. So that's the final answer of the counting problem via the traditional way. So this is what we have done. We started with a counting problem. We set up a recurrence for the sequence. We get an equation, a functional equation for the generating function. Then we find a closed formula, and then the asymptotics. So this is one way to count. And now I'm going to show you another one, which is based on, well, it splits in two parts. The symbolic and the analytic. You will see that in the symbolic, we're going to define a combinatorial construction following what in formal languages is like a formal grammar. Something very similar to that. And then I'm going to show you some symbolic transfer theorems that from the combinatorial construction will give the equation for the generating function. And then I will show only one analytic transfer theorem. There are several that directly from the equation for the generating function gives you, well, it's really from the closed formula for the equation. I didn't want to put another box for the closed formula, but anyway, but you don't need a closed formula for the sequence to get the asymptotics. Okay, so let's start. So we need to define a combinatorial class. That's a set plus a function that tells you the size for each member of the set, and it has the property that the number of elements of A that have a given size is finite for every natural number. Okay. Well, in analysis of algorithms, for example, this would well, in analysis of algorithms, you have the input size, and you have a cost function that gives you a measure of the cost of running the algorithm for a given input size. And there are two branches of analysis of algorithms: worst case and average case. The worst case analysis of algorithms is analyzing the sequence of maximums of cost for every input size. The average case is giving a probability distribution for the size of the input. Is the average, the expected value, or the sequence of the expected values for the n. Anyway, but in general, you have a measure of the size. So, well, some notation. We use a sub n to denote the number of elements of A that have size n, and if when it's clear, we will simplify the notation. So then the generating function of A is this formal power series. Well, this is the standard way of defining it, but this form of defining it is really useful. You will see, and it's easy to see that both are the same, no? Because A sub n is the number of members that have size n. So, okay. As an example, trivial. All my examples are pedagogical or toy examples in this talk. Okay, so let's say the A is the set of bit strings. So A sub n. Here are the very first examples. We use this epsilon to denote the empty string. Okay, which in programming languages would be like quote unquote in many languages. Okay, so these are the sequences of bits, and A sub n trivial is 2 to the n, and the generating function has this closed formula. All this is trivial. Okay, so let's define some operations on combinatorial classes. So the disjoint union is when the two sets are disjoint, which will be the case for all the examples I'm going to give. It's just a standard union, and if not, it's a multi-set union. And the size of the union is, well, is what's explained here. I mean, it's given by the sizes of the two sets that you are uniting. So, well, as an example, I mean, you have this set, and you just do the union, and well, and here the generating functions of those sets are these, and the generating function of the union is the sum of the generating functions, and it's easy to see. I mean, that's a general theorem. I mean, trivial. I mean, to prove that that's in general the case, that the generating function of the union, of the disjunct union, is the sum of the generating functions. So another operation is the concatenation, which is very similar to the Cartesian product, but I prefer the notation of concatenation. I mean, if you think of strings, you are just putting them together. And the size function is the sum of the sizes. Okay. Sorry, were you able to see the screen before? Because it's telling me that now you can see the screen. Well, I hope you were. Okay. So the neutral element of the concatenation is the set that has the empty string, or the neutral element. Well, anyway. So here is an example with three sets. Well, it's very easy to see that this operation is associative, and you could define it for k elements easily. So here I'm doing the concatenation of the set with empty string, the set with bits, just one bit, or the set of sequence with just 2 bits. And well, it's clear you get a set of sequences with 3 bits. And then in this case, the generating function of the result is the product of the generating functions. And that's also a general result. The generating function of the concatenation is the product of the generating functions. And again, well, in this case, when you use this definition of the generating function, it's very easy to see. I mean, because the size of this is the sum of the sizes, and then you just take common factors. I mean, okay. If you have any question, no, fine. Okay. Now, a third operation is a unary operation, which is the sequence of, given a combinatorial class, the sequence based on that combinatorial class. And that's defined as, that's a combinatorial class that has no element of size 0, okay? So that's just defined this way. I mean, the empty string, or A union with A, union with A squared, A cubed. So in this case, if A is 0, 1, then C is the sequence of the bit strings, no? Which, as we saw before, has this generating function. Now, again, notice that all what we did was put 1 over 1 minus the generating function of A. That again is a general result. And it's just from, I mean, given the previous 2 results, it's just the geometric series. Okay. Now, there is another way to prove this, which is to define recursively the sequence of elements of A as either the empty string or an element of A followed by a sequence of elements of A. This is more like what in formal grammars is done, and that leads us to this combinatorial construction. And then when we apply the previous 2 results, we just solve for C set, and we get the same result. Okay. Okay. So I have shown you 3 transfer theorem, a transfer theorem with 3 parts. But this is just the tip of the iceberg. Okay. And obviously we don't have time to go into more things, but just so that you get some flavor of other things that can be defined. And I mean, like other transfer theorems. I mean, you can talk about the power set, the multi-set, the cycle, these fees, I think the Euler Totian function. But anyway, we're not going to go into any of this. Okay. Now, as an example of a symbolic transfer, let's look at this counting problem, like how many bit strings of size n do not have two consecutive zeros. And one way, I mean, there are several ways to do this, but one way is to define the class of bit strings that satisfy that property recursively. I mean, you either have the empty string or you have just 1 0. And then if the first bit is 1, then the rest is another member of G. I mean, we don't have any restriction about the rest of the string. But if it starts with 0, the second bit has to be 1, because we do not want two consecutive zeros. So, but after we have that 1, then the rest is an element of G. Well, this leads to this combinatorial construction. And then applying the transfer lemma, we get the functional equation, which we can solve. And if you recall the Fibonacci number generating function, which is set over that. So you can split this into 1 over that and set over that. And that 1 is the Fibonacci sequence shifted 1, and that's the other is the Fibonacci sequence. Well, and when you add 2 Fibonacci numbers, you get the next Fibonacci number. Well, that's why you get Fn plus 2. Now, a quick comment about formal languages. So this is an example of a regular language, which are the simplest languages in Chomsky's hierarchy. And the regular languages always lead to rational generating functions. Well, you could, if you were to put define the recurrence, it leads to linear recurrences, and linear recurrences always lead to rational generating functions. And well, I just want to show for those of you that are familiar with the Chomsky's hierarchy that there is this relationship. And for me, that was like a surprise, because back in the 80s, for me, formal languages were one thing, generating functions another word. I think the next level in the hierarchy are context-free languages, and I think they lead to algebraic generating functions. Anyway, now let's. I would like to give you. So what I have talked so far is about the symbolic method. So now I'm going to move into the analytic part. So for this, we stop considering the generating functions just formal power series, and now we consider them as complex value functions. And for many counting generating functions, we have that the coefficients, well, or the sequence that you are analyzing, have this form where k is a constant and g sub n is a, let's say, sub-exponential, I mean, so a factor that grows less rapidly than the factor k to the n. Okay, and two takeaways. I mean, two important messages that you can take from this talk. Well, is that the locations of the dominant singularities of the generating functions immediately provide you information on the asymptotic exponential growth, and that's not new from analytic combinatorics. I mean, that's something known before. But what Flageolet and Oldisco achieved, well, I'll talk more, is that they gave. Well, I'll explain that more later. But the local behavior of the generating function around the dominant singularity is what gives you this sub-exponential factor. Okay. As a trivial example, let's look at the Fibonacci function. You can factor the denominator this way, and that gives you the two singularities. I mean, the golden ratio and the conjugate, I think they call it. I'm not sure. Anyway, so when you plot that complex value function, well, you have these two singularities, and the closest one to the origin. Well, the singularities are the inverse of these two numbers. No, I mean, I have written it this way so that the singularity phi to the -1 is the one closest to the origin, and that is the one that gives you the asymptotic behavior. Obviously, you could have done this. I mean, you could decompose this with partial fraction decomposition. You can get this result elementary. Well, actually, let me show you another elementary case, just to give you again another toy example of cases when you have more than one dominant singularity. So let's say that you want to find a closed formula for this periodic sequence. So you can define the generating function equation, and then you can solve for it, and then you use partial fraction decomposition. So in this case, the 4 singularities are the 4th roots of unity. No? So 1, -1, I, and -I, and you get this closed formula. Yeah, I mean the period was 4, and that's why we get the 4th roots of unity. You know, if you have a periodic sequence with period k, then you get the kth roots of unity. Okay, so brief story of singularity analysis. I mean, in 1918, Hardy and Ramanujan applied Cauchy's integral formula to get the asymptotics for the partition function. Then over the decades, that was improved. Well, in 1956, Hyman applied like a new method, saddle point method, to generalize Stirling's formula. And in 1990, Flageolet and Odlyzko, in this paper, which is like seminal on the analytic combinatorics field, they got several transfer theorems to translate the generating function expansion around the dominant singularity into the coefficient asymptotics. And actually, they can generalize that to not just a single dominant singularity, but more. Well, yeah, and sometimes they look even to singularities that are beyond them if they want not just the leading term of the asymptotic expression. Anyway, so just so that as I said, I'm going to give you just one analytic transfer theorem. I mean, there are several, and this one, what it says is that if you have the generating function of this shape, where the numerator has a radius convergence larger than the radius of convergence of the denominator. So the pole of the denominator is rho to the -1. So all what that's saying above is that the numerator has a radius of convergence larger than the denominator. And this alpha is any real number, okay? So if that is the case, then the asymptotic, well, and with this condition, the asymptotics of A sub n are these, no? Where gamma is a gamma function. Okay, so you get the exponential growth and you get the sub-exponential factor. Okay. Any question? Okay. So let's go back to our original problem. So the counting the polygon triangulation. So the first step that we need to take is to find the combinatorial construction for this. And for that, we can define the polygon triangulation recursively the following way. It's either a segment of size 0, no, which was in this case, or it can be decomposed into 3 parts: the triangulation on the left, one triangle, and the triangulation on the right. So the combinatorial construction is this one. Okay. So that's our combinatorial construction. Then we apply symbolic transfer, and we get the generating function equation. We solve that, we get the quadratic formula, and then we apply the analytic transfer theorem, and that's it. Boom, boom, boom. So this is what I call, I mean, this is a the other way to count. I mean, I think it's very elegant. I mean, you don't need to do all that algebra that I show in the initial slides. You don't need to worry about the recurrence for the sequence, neither for finding a closed formula for the sequence. Any questions or reactions? I'm not sure if Elbar, you want to say something, but you're muted.
No, I'm just interested.
Okay. Okay. So now you understand better what I mean by this other way to count, no? And I just want to emphasize in the slide, I mean, the relationships to some of the things that I mentioned in the description of the talk. I mean, formal languages are like what you use to get a combinatorial construction. Then enumerative combinatorics, they have there all these symbolic transfer theorems, and then the use of complex analysis, similar to what is done in analytic number theory, is what I mean, because there, again, the generating functions are seen as complex value functions, and they apply all these theorems from complex analysis. Well, that's what allows to go directly from the well, in the case I show, it was going from the closed formula for the generating function to the asymptotics. But there are cases when even if you cannot solve, I mean, if you cannot solve for the generating function, sometimes if it's given just implicitly, you can get the asymptotics. Okay. Okay. So now I would like to pose the two problems. So the first one is a variant of Monty. I mean, it's really different. I mean, in this case, you have behind the three doors, instead of two goats and a car, you have behind one door you have the car. Behind another door you have the car keys, and behind the other door you have the goat. And obviously the organizers put them randomly there. And then, but now there are two players which play like a team. When the first, and they go into a stage in sequence. Okay, the first player comes to stage and he opens one door, and then he opens a second door, and then they close the doors. He leaves the stage. And the second player comes and does the same, opens one door, opens another door. Okay. And they win the card if the first player opened the door that has a card, and the second player opens the door where the card keys are. So obviously, once the game starts, they cannot communicate with each other. I mean, player two cannot see what player one, I mean, is seeing when he opens the doors. So they cannot communicate with each other once it starts, but before they can agree on a strategy. And the question is, what do you think would be the best strategy that they can, I mean, the one that would give them the highest probability of winning the card? And I love this problem because it's I mean, you can do it like on a meal table. I mean, lunch, dinner. I mean, there are so few cases to analyze that you can analyze them on a napkin. I mean, if people propose you any strategy, well, crystal clear, the strategy of picking the doors random. I mean, because each player has, in that case, well, 2/3 chance of opening the door, or opening the right door, you get a 4/9 probability of winning. But I don't know, any suggestion? Well, given that we don't have much time,
the only choice you've got is either whether you leave one of the doors completely unopened, right? Because you open two doors, two people. So either you overlap in one door, or you overlap in two doors. So it's a question of whether you're better off overlapping in two doors than overlapping in one door.
Okay, so I think when you make the numbers, so we are saying one strategy could be both open doors 1 and 2, and another could be one. Let's say player 1 opens doors 1, 2, and player 2 opens doors 2, 3.
Yeah, then they overlap in one door.
Yeah, when we do the math, strategy 2 is better. I mean, of the two that you are proposing, strategy 2 is better, and it gives you 50% chance.
Right.
But you can do even better than that, David. Okay, so more surprising, I mean, there is a related problem. The 100 prisoner problem, maybe some of you knows this. This one is the following. You have 100 prisoners, and the guards have decided to play the following game with them. I mean, to give them a chance to freedom the following way. They have these drawers, 100 drawers, and in the drawers, they put in each of them a piece of paper with numbers, natural numbers, from 1 to 100, in a random way. And then each prisoner, so prisoner 1 comes to that room on his own, and he can open 50 drawers. And then they close them and he leaves. Then prisoner 2 comes and does the same, and so on. The 100 prisoners have the chance to open 50 drawers. But again, it's in sequence, no? And they cannot communicate with each other. And they gain freedom if prisoner 1 opens the drawer that says 1, prisoner 2 opens the drawer that says 2, and etc. I mean, if all the prisoners, the prisoners have a number, okay? So this is prisoner 63. They have hats with the numbers. So if all the prisoners open the drawer that has the number in their hat, then they are free. And again, once this starts, they cannot communicate, but beforehand, they can agree on a strategy. And the question is, what's the best strategy?
I mean, surely you've got half a chance of, like, each prisoner's got half a chance of getting their number right. So, yes. Seems very unlikely then, like, isn't it like 1 over 2 to the 100?
No, they can do better.
Much better.
If each prisoner opens the drawer with their number on it, and then open the drawer that has the number that is inside of that drawer, so they, and then they go into a cycle.
Okay, yes, that's the answer. What Karin has described is the answer, but to analyze it using analytic combinatorics, I'm going to introduce you. What we were talking before are called ordinary generating functions. These are the exponential generating functions. These are used for the case of labeled structures. I mean, when you, like, for example, in the polygon, the vertices of the polygon were indistinguishable, no? But if we were to label them from the numbers 1 to n, I mean, you could distinguish them. And in general, when you can distinguish the atoms that form the structure, obviously you have n, but I mean, if you have n atoms in a particular structure, you have n factorial ways to label. And then what happens is that the ordinary generating function grows too fast. So and then you don't get conversion. But by dividing by n factorial each coefficient, you that's much better. I mean, and you will see. And I don't have time to explain too much here. I mean, I'm going to show you some things without proving and maybe probably properly defining them. But well, you can imagine the set. What's the meaning? And cycle is like a circular permutation. Okay. And believe me, these are the generating functions. Really, well, something, I mean, for example, for the cycle, you know that how many permutations you have, circular permutations you have with k numbers is k minus 1 factorial, no? So in that case, a sub n would be n minus 1 factorial, and when you divide by n factorial, you get this, no? And well, and this series has, I mean, close formula. Okay. And what is crucial for to understand the solution that Kari proposed is to think of permutations as set of cycles. Well, I'm not sure if all of you are familiar with this notation, but I'll explain it quickly. This means, because a permutation is bijection, in this case, of the numbers 1 to 10 to itself, no? And what this is saying is that 1 goes to 3, 3 goes to 5, 5 goes to 1. And then 2 to 10 and 10 to 2, 4 stays, I mean, f of 4 is 4. Well, allow me to talking not in terms of function. Then 6 goes to 8, 8 to 9, 9 to 7, and 7 to 6. So that, and you can always see a permutation as a set of cycles. And with this combinatorial construction, we can quickly, I mean, given the transfer theorems that I show in the previous page without proving them, well, the set is exponential, and this one is the cycle, and well, they are one the inverse of the other, and you get this, and you get, well, as you expect, that the number of permutations of size n is n factorial, because well, this has the series 1, 1, 1, and then p sub n is exactly that. Okay, so for the 100% problem, well, Kari already explained the strategy, but let me explain in case somebody has a, let's say there were only 10 prisoners, okay? And they can open 5 doors. So if prisoner 1 opens the drawer number 1, then that drawer will have the label 3. Then he will open drawer 3, that will have label 5. They will open label drawer 5, and I will have label 1, and that's it. The prisoner 1 got his number. Here, player 2 would open drawer 2, and it will say 10, and in drawer 10 is 2. Player 4 would open drawer 4, and it says 4, and so on. So in this case, with each prisoner opening 5 drawers, they will gain freedom. Is clear? Okay. I know it's similar. I mean, with 100, it's the same story. But okay. So if we say that f sub n is the number of permutations from 1 to n with no cycles of length greater than 50, and I'm saying greater than 50 because the only way, in the case of the 100 prisoner problem, the only way that they lose if the permutation has a cycle of size greater than 50. So to compute the probability of winning, we are interested in the cycles of size less than 50. And that's why instead here of the sum, the infinite sum, I only have the first 50 elements. Okay. So then this coefficient a sub n over n factorial, because when I said the permutation that the guards put in the drawers is random, I mean, well, so any of the n factorial permutation has the same probability. So this a sub n over n factorial gives you the probability. I mean, in particular, the probability of no cycles of length greater than 50 is the coefficient of set to the 100 in this generating function. Because set, that 100 gives you that is the number of drawers in total. Okay. And because we have restricted this to 50, is that well, and then obviously I'm running out of time. But after some algebra, I mean, probably you can use computer algebra, some computer algebra software. You can find that coefficient is 1 minus harmonic number 100 minus harmonic 50. The harmonic numbers are like the discrete version of logarithm. And I mean, they are very close to it. Well, so it's approximately that, and that is 1 minus 1. And so the probability of freedom for the 100 prisoners is like 31% following this strategy, which is surprising. I mean, because when the first time you see this problem, I don't know if Kari, you knew the problem before, or you just saw about it.
Yeah, I knew it.
Okay. Because yeah, well, I don't know any person that the first time, your first reaction when you see the problem is to think, oh, 1/2 to the 100, and it's hopeless.
So when do they get free?
When each of them opens the door that has the drawer with his number. So you saw why in
and then after each one has been, they close all the drawers again.
Yes. So I describe here the case with this example, the case of 5 prisoners.
When you say someone is free, you're talking about all of them?
No, all of them.
So you're saying if we do this, then all of them get free?
Well, the only way for all of them to get free is that all of them open the drawer that has their label.
Yeah, that's what you're talking about, that they all get free.
And they all get free. And well, I analyze. Yeah. So you see here 10 drawers.
Yeah.
And like each player, because the cycles, the maximum cycle here is size 4, opening 5 drawers and following the cycle, they will manage to get their number.
Okay, so let me take this here, right? So number 10 goes first, okay? Number 10 goes first. He does 1, 3, 5, and then he follows.
No. Number 10 opens drawer 10. He starts by opening drawer number 10.
Which is 7 here, is that right?
No. In this notation says, in drawer number 10, I mean, you have this circular permutation with these 2.
Yeah. In drawer 10, it says 2. So you open 2, and 2
says 10.
Says 10, okay? But number 10 goes and opens drawer 10. So number 10 goes along and starts. And he opens drawers 10, and that says 2, and number 2 says 10. Okay.
And that's it. That he managed to get his label.
But number.
Okay, so tell me another of the 10 ones.
Okay, so I'm looking at.
So let's say player 7. I mean prisoner 7.
7 opens it and he finds
6.
And then 6, 5, 7, he gets that. Okay, I see. Yep. So what you're saying is that the permutation chain that takes him to his own number has that probability to 0.31.
Well,
the other way around.
Well, this is the probability that the permutation has no cycle of greater than 50.
Right, which is
the probability of winning.
Himself, right?
Yeah.
Within the 50.
Yes. So they, with this strategy, they have 31% of probability of all of them finding their number.
Yeah.
Okay. And now going back to the variant of Monty Hall. Well, this one is really the same problem. All what you need to do is to codify. You say car is number 1, keys is number 2, goat is number 3. So you see, all what I was saying is player 1, I mean, once you say car is number 1, player 1 has to open the door with number 1. And player 2 has to open the door with a key, or player 2 has to open the door with number 2. So, and the strategy is the same. They follow the cycle. And, well, and you can see easily, and the only way that they lose is if the organizers use a permutation with cycle 3, which are the bottom 2. But with any of the other permutations, they win. So the probability of winning is 2/3 following the cycle. So it's the same problem in disguise. And by saying Monty Hall, I mean, you confuse people.
Yeah, no, I see that. But I think the interesting thing here is back to the whole combinatorics, and it's really that combinatorics severely restricts your space, right? The space of permutations.
Sorry.
That's what gives you the gain.
Well, sorry. Here we are allowing all 6 permutations. I mean, we are not restricting them. No, I mean, it's just that we're looking at.
But when you follow your permutations, what I mean more precisely is not that they, they get you to everywhere in that sense. But what I'm saying is that they,
well, you're looking to by looking at it this way, you are like looking at the structure of the permutation and taking so because normally you would think, I mean, before looking at this way, I guess, oh, you open one door and you have no information, but there is really some information. I mean, so the decisions that the 2 players are making are not really independent with this strategy.
Yes.
Because obviously, if you say, oh, the 2 of them open 2 doors randomly, then okay, then the decisions are independent and you multiply the probabilities. I mean, they still have each of them independently two-thirds of getting the right door, but because you have taken advantage of the information, the 2 probabilities are not independent. Well, anyway, do I have something else? Oh, yes. Sorry. Very briefly, I wanted to mention that, I mean, there are many, many things. As I said, I'm just showing you the tip of the iceberg. I mean, there are many more symbolic constructions. You can get implicit results applying this theorem. Then, oh, there are bivariate and multivariate generating functions. For example, when you analyze binary trees, parameter that is interesting is the height of the tree, and so that you can model that with two variables. I mean, like you could, besides having set to the n, where n is the number of nodes in the tree, you will have another variable u to the k, where k is the height of the tree, and well, you can work with.
So I think what I wanted to say was essentially what you're saying is by having an agreed labeling of the boxes, it allows you to work along a common set of permutations, which is what limits it down.
Yeah, we agree.
Yeah.
Sorry. And so this is something that started in analysis of algorithms. And nowadays, well, as you can see, there are presentation papers where they are applying it to combinatorial physics. I think that I don't know much, I don't know anything, but I have heard that there is something called quantum walks, like the quantum version of random walks, and they apply that. I mean, just like you count random walks, you can count quantum walks, or well, in mathematical biology. Well, in chemistry, I know that Paul's enumeration theorem, he used it to count number of chemical compounds. Well, I mean, any field where combinatorics has been applied, I think we can agree. You can think that maybe analytic combinatorics can be applied there. So this is a very active research field, and I'm going to make available this PDF in my website, and I give you the links to the books by Flageolet and Sedgwick. I mean, this one is like the Bible. I mean, this was the one they published in 2009. Was like, I mean, the reviews were like, oh, this is a book that is like defining a subfield. And here is the link to the A of A, I mean, community, and they would welcome anyone interested in doing research here. And there are Coursera courses, plenty of YouTube videos, and that's it. I mean, so sorry. I didn't leave so much. But now we're open to Q&A. I mean,